All right, in this video, I'd like to talk about section 2.5 and 2.6. So chapter 2.5 is on acceleration. And acceleration occurs when velocity is changing. Right, we already mentioned before that a constant velocity implies that acceleration is 0. So we have a non-zero acceleration when the velocity is changing. We define our average acceleration similar to how we defined average velocity. So A in the x direction average is defined to be delta V in the x direction over delta t. So a change in velocity over a change in time. And right now we're talking about in one dimension, which I've called the x direction. So a delta is a final minus an initial. So we have a Vx final minus Vx initial over T final minus T initial. And as usual, we're probably going to call our T initial 0 and just our T final T. So we could even say that this is just a delta V over T. Sorry, my phone's ringing. All right, and as we consider an instantaneous value rather than an average value, that's our limit, right? So we're going to take the limit as our time interval goes to 0 of delta V over T. And that, of course, is our derivative. Few things to observe. A is a vector. And that means that it has a magnitude and a direction. Magnitude, again, just means its size. That's the numerical value associated with it. And if we're talking about in one dimension, forever now written as 1D, we use plus or minus to indicate direction. For example, if I call this my positive x direction, then this is a positive ax and this is a minus ax. We've talked about a lot about graphs. So what I want to do is I want to take an example of A versus T. And I want to translate that into our V versus T graph and X versus T graphs associated to this acceleration. Let's look at a V versus T. All right, so we're starting out with a positive constant acceleration. So that means our velocity is increasing at a constant rate. And we can start it wherever we want, right? We've talked about this. We don't know what the initial velocity is. The acceleration only tells us how the velocity is changing. So I'm going to assume that my V naught is just some value here. And let me sketch in some scaling here. There we go. So during this first region, when we have a constant positive acceleration, v is increasing at a constant rate. Then when acceleration is 0, we know that we have a constant velocity. So constant velocity while acceleration is 0. So let's call this region 1, region 2, and region 3. So in region 1, positive constant A implies linear increasing v. In region 2, A equal to 0 implies constant v. In the final region, we have a negative A, and it looks a little larger valued than the positive A we had before, so it might be a little steeper. All right, something like that. So in region 3, negative constant A gives us a linear decreasing v. And let me resketch my v since I'm moving down to a new page here. And I want those to be correlated too. So what does an x versus t look like for this? I'm going to start again with a x naught here so that I have plenty of room to draw. And again, we'll call them region 1, 2, and 3. So in region 1, we have a linear increasing v. And that's going to give us a quadratic x that is concave up. Right, remember your second derivative test from calculus? Acceleration is the second derivative of position with respect to time. So it gives you the concavity of your x, right? And you can also think of it in terms directly from the v graph. The velocity starts out negative, right? And then at some point it's going to be 0, and we have our turning point, and then it starts going up, right? So during this first part of our graph, we have something that's concave up the entire time. There's no point of inflection, but there is a 0 slope point associated to the 0 in v. During region 2, we have a constant v, constant positive v, which is going to give us a linear increasing position. Guess I don't need a, there we go. So this part should be linear, and it should be the same slope that it ended with there. All right, during region 3, our velocity is linear decreasing. So that's going to give us an x that's concave down, right? Again, our x will be quadratic and concave down. So let me sketch in our 0 point there. And it's smooth, right? There are no jumps in our velocity curve. There are some hard corners here, but there's no discontinuity. So that means that our X graph should be smooth. So it's going to go up at that same speed, but that speed's going to slow down, slow down, slow down, hit 0, and then turn into negative speed values. So our slope's going to go down. Right, but you'll notice that during each linear region of our V graph, the concavity doesn't change. When V is increasing, we have a concave up region. V is constant, you have a linear region, and then when V is decreasing, you have a concave down region. All right, so that's everything I want to talk about associated to 2.5. Associated to 2.6, I wanted to talk a little bit about the motion diagrams here. And this section talks about what you would call stroboscopic diagrams. Right, stroboscopic, so you're thinking like a strobe light. Right, so imagine you have something moving and you have a strobe light blinking. So you can only see where it is when the strobe light is on. So if we were to have a constant V and we observe something moving with this stroboscopic lighting, the light blinks and we see it here. The next time the light blinks, it's here. The next time the light blinks, it's here. The next time the light blinks, it's here. Next time the light blinks, it's here. And the intervals between each are the same. So if we look at next an increasing V, and we again look at that strobe light, initially it's here. Next time it blinks, it's here. Next time it blinks, it's here. The next time it blinks, it's here. And the next time it blinks, it's here. And you can see that we have increasing distances traveled in each unit of time, right? This stroboscopic effect, we're saying each snapshot is taken with the same time interval. So the distance intervals are increasing over the same time intervals as our speed is increasing. And we get the same effect for a decreasing V, but in the opposite direction. So let's say we start out at a high speed. So the first time it blinks, we've moved over here. The next time it blinks, we move over here, and so on. And we come to a stop, or not necessarily a stop, but we slowed down. Right? If we continue long enough, it would come to a stop. So this is what you would call a stroboscopic motion diagram, and it's a good way to visualize what's going on, because when you see this even spacing, you get that idea of constant velocity. And when you see the uneven spacing, you can get a sense of it's increasing in speed or it's decreasing in speed on the spacing.